Good morning. This is the AP Calculus video for section 5.3. As you can see, it's called separation of variables, which is a technique we will use to solve certain types of differential equations. So let me start by reminding you that we know how to solve differential equations. If I'm given the differential equation y prime equals 3x squared, I just integrate. Just to solve for y, I would just integrate. And so it would be the integral of 3x squared dx, which would just be 3x to the third over 3, and the 3's cancel. So it's just x cubed plus 3. Like that's an example of solving a differential equation, and we've done many like that in taking all of these antiderivatives. So today we're looking at an equation like what? Like the one at top there, y prime equals 2x over y. And the fact that the function on the right has both x's and y's, I can't just take the integral of that because I don't know how to take the integral of 2x over y. So here's where this technique of separation of variables works. And here's kind of the process we're going to follow. It says before integrating, we need to separate the variables. First, we're going to rewrite where it says y prime. I know that you know that an equivalent form to y prime is dy dx. We're going to write it as dy dx because then I can algebraically separate the dy and the dx. So we're going to rewrite the y prime as dy dx, and then we're going to do some algebra, and we're going to get all the x's and the dx on one side of the equation and all of the y's and the dy's on the other side of the equation. That's the separating the variables portion. Once we do that, we're going to integrate both sides. And what you'll see here is that both sides need to be integrated separately, not just the right side, it's both sides. And then after you do that, we're going to solve for y. So I have a few examples where we'll do that. And of course, these will at first be the general solutions. So there will be a plus c at the end. And then, like with other differential equations, we will then find the particular solution. So let's look at the same example. So I rewrote where it says y prime equals 2x over y. I rewrote the y prime as dy over dx, which is there. And now I'm just doing some algebra. Let's see what I did here. First, I just multiplied the dx over the right side, so I did there. And then dy equals 2, there's a typo, this should say 2x over y dx. I haven't messed with that y yet, sorry. And then I multiply the y to the left side and get y dy equals 2x dx. So this line right here, I have in fact successfully separated the variables. I have the x's and the dx on one side, I have the y's and the dy's on the other side. Once I get there, now I integrate both sides. So that's where the purple integral signs come from. Now I take the antiderivative of both sides. And each side is going to have an antiderivative. So on the left side, the antiderivative of y dy, well, that's just a simple power rule. That's just y squared over 2. And then the right side, the integral of 2x dx is just x squared plus c. And then you'll notice I say here, officially both sides would have a plus c, but you could always just subtract the one c to the other side and it becomes just plus c. So we're always just going to put the plus c on the right side. And once you do that, now let's just solve it for y. So a little bit of confusion. On this line here, I just multiplied both sides by 2. There's no reason to put plus 2c because 2 times a constant is still any constant. And then sometimes you'll actually see it finished as y squared, but normally it'll say to solve for y. So I just square rooted it. I get y equals plus or minus the square root of 2x squared plus c. Notice the c is allowed to kind of be wrapped up in your final answer. Not a problem there. So there's the first example of solving a differential equation using separation of variables. Okay, a few more examples to do because there's a couple other common issues that show up we need to know how to handle. So let's look at this one. It says x squared plus 4 times dy dx equals x times y. Notice this one already had the y prime written as dy dx, which we like, so we'll just leave it like that. So let's see what I do first. First, I just to get to this line, I just multiplied the dx to the right side. And then what I do, then I divided both sides by y. That got the y from the right side to the bottom of the left side. That's this line here. And then I divided both sides by x squared plus 4 to get the x squared plus 4 from the left side to the bottom of the right side. So this line right here I have the variables separated. Now I'm going to integrate both sides. And what you have to recognize here is this left side is pretty easy anti-differentiable. The right side, we're going to have to use a u substitution, which we just learned. So think on the next slide, I write the integral sign, which I did there, up there at the top. Now this right side, I had to write a u substitution. So I called u equals x squared plus 4, and I forgot to circle these up here, so that makes this thing here u. The derivative of u is 2x dx. That 2 is kind of in the way, so it's 1/2 du. So now this x dx, I'm going to substitute as 1/2 du. That's a 1. There we go. And so now I'm just going to rewrite my right side as, as 1/2. So there I rewrote the right side in terms of u, 1/2 integral of 1 over u du. And then the left side I left alone. Now I can integrate both sides. And the left side, when I integrate 1 over y dy, well, the antiderivative of 1 over y is natural log of the absolute value of y. And then similarly, the right side, the integral of 1/2 integral of 1 over u is 1/2 the natural log of the absolute value of u. Notice I went ahead and replaced this. Originally would have said natural log of u, but I replaced u with what u equals. So there. So this line here, just put an arrow, the yellow arrow by. I have finished integrating both sides. Now the goal is to solve for y. So you need to remember algebraically that if it says the natural log of y, and I want to undo that by taking e to the left side and e to the right side, that will solve for y, because e to the something, the exponential function, and natural log are inverse operations. So I e both sides, for lack of a better word. Now, let's talk about both sides separately, because both sides have an issue here. This left side, when you e to the natural log of y, that's just going to become y. Like e to the something is always positive, so that kind of eliminates the absolute value sign. Let's look at this right side. So I need to remind you something. Remember this rule of exponents. I'll come back to that slide in a minute. If I have x to the second times x to the fifth, I know you know that's x to the seventh. But I'm going to write it like this. Like really, I'm adding exponents. And of course, I would write that as x to the seventh, but I am adding exponent. And in particular, I want you to recognize that if I have something that looks like this, I can write it like that. If I have x to the 2 plus 5, I can write it as x squared times x to the fifth. I'm going to use that property in that direction back here. So let's go back where I was. Okay, let's compare this yellow line. Let's compare this line up here. Oh, I meant to do yellow. Let's compare this line to the line below it. I have e to the something plus something. And using that rule of exponents, that's e to the first thing times e to the second thing. So let me highlight. I have e to the, change colors here. I have e to the this whole thing. There's e to the that. And then what was plus that, I wrote as times e to the that. Like that's using that rule of exponents. That x to the 5 plus 2 is x to the fifth times x to the second. This is a fairly common thing to do when you're having to undo these natural log by eing both sides. And now I can clean this up because this number right here, e to the c, is still just some constant c. So that moved, I just wrote it in front. So it's c times e to the 1/2 natural log of x squared plus 4. And I also did some sneaky rules of logs. This thing where I've gotten this in this blue rectangle here, the rules of logs, I could write that as, instead of 1/2 natural log of x squared plus 4, I can move that 1/2 out front as an exponent. So the natural log of x squared plus 4 to the 1/2, which is the square root. So that's where this square root sign came from. And now, conveniently, the reason I want to do that is because e to the natural log of something, those are inverse operations. So now you'll notice the e to the and the natural log go away. My final answer is just y equals c times the square root of x squared plus 4. So a couple things going on there that are pretty common. One is when you've got this whole e to the something higher. When you've got e to the something plus c in particular, writing is e to the first thing times e to the c. And then that e to the c over here just became my constant c. And then I use rules of logs to help simplify that. So there's that example. A little confusing, but again, that concept shows up fairly regularly. All right. Next one. I think I've got just two more. I forget. All right. It says xy prime equals y. First, as I said right at the beginning, we're going to rewrite y prime as dy dx. That's all I did there. Now let's separate the variables. So I multiply the dx over to the right side. That's this one. And now both variables, the x I need to move over to the right side by dividing by x, and the y I need to move over to the left side by dividing by y. I did those both in one step. So I end up with 1 over y equals 1 over y dy equals 1 over x dx. I have successfully separated the variables. Then I integrate both sides, which I did here. And all I did was write the integral sign. Both of those are identical. They're both natural log of the absolute value of y equals natural log of the absolute value of x. We'll put the plus c at the end. Now you'll notice I am in fact going to e both sides. The left side conveniently just becomes what was e to the natural log of y is just y. And this right side, I don't want to show you what I wrote yet, but here we go again, where this thing here is e to the something plus something. So using the rule of exponents, that should, what I'm hoping I wrote in the next line is e to the natural log of the absolute value of x times e to the c. Like, I hope that's how I wrote it next. I may have simplified it because remember that e to the c is just a concept. I think I wrote it like that. Let's scroll down here and check. I did. Good. So I'm glad I wrote it like that. And then I can do two things. That e to the c at the end, that's just a constant. I'll move that before the first e. And the e to the natural log of x is just plain old x. This thing simplifies very nicely to y equals cx. Excuse me. So there's that example. And then the last thing I want to show you is what about finding a particular solution? So this is not a new concept. We've done this before. It says, as with other differential equations, if we are given an initial condition, which just means an ordered pair on the graph of the original function y, we can use that information to solve for c. And this is called finding the particular solution. So same thing we did, but we're going to be able to find c. And I'll say this now, and we'll do it again in the example. So here's what we're going to do. We're going to separate variables. We're going to integrate both sides, just like we did before. And then we'll have this equation with a plus c. We'll have two things left to do. We'll have to solve it for y and find c. And you can officially do both in either order. I'm telling you, it's going to be easier to, before you solve it for y, input the x and the y, solve for c, and then go back and find y. And you'll see that in the example we're going to do here. So here we go. Last example, I think. It says find the particular solution of dy dx equals e to the y minus 2x, given the initial condition y of 0 equals 0. All right, so let's separate the variables. So this line right here in red, all I did was move the dx to the other side. Now, in order to separate these variables, I have this e to the y minus 2x. We have to be able to separate those somehow. So let me go back to rules of exponents for a minute. Let me again remind you that if I have x to the 5th over x to the 2nd, I can write that as x to the 5 minus 2. I can subtract exponents. I know you know that rule of exponents. You've known it for years. What I'm going to do here is I'm going to essentially write this as x to the 5th over x to the 2nd. I'm going to use that rule of exponents. So over here, again, I'm going to rewrite this thing right here where it says e to the y minus 2x. I'm going to rewrite that as e to the y over e to the 2x. That's just a rule of exponents thing. But by writing it like that, now I can separate the variables, which means the e to the y on the right side, I have to move to the left side by dividing by e to the y. So that's where this line comes from. I have 1 over e to the y dy equals 1 over e to the 2x dx. I have successfully separated the variables. And I'm going to rewrite both of those as negative exponents, which I did right here. Before I wrote the red integral signs, I just wrote as e to the negative y dy equals e to the negative 2x dx. Now I am, in fact, ready to integrate both sides. So I put those red integral signs. Now I want you to recognize that both of those sides of that equation, the left and the right, require a u substitution. So don't forget all the things we've already known. So I think I did that here. So on the left, here's my u substitution. Notice that both sides of this equation are going to turn into an e to the u, like it's just a matter of using the right u substitution. So on the left side, u was negative y, the derivative was negative dy, that's this. That negative sign I moved to the left side. And so that enabled me to write this as, there's this first one rewritten in terms of u. And then over here, I'll change to green. U was negative 2x. The derivative is negative 2 dx. That negative 2 I had to move, negative, if I multiply by negative 1/2, that became this. And I was able to write this as negative 1/2 e to the u du. So both of those, other than the negative sign of the negative 1/2, turned into an e to the u. Remember how much we like u substitution, because the integral of e to the u du is just e to the u plus c. So these both become just e to the u. And then you'll notice I, in both cases, replaced u with what u was. So on the left side, I have negative e to the negative y, and on the right side, I have equals negative 1/2 e to the negative 2x plus c. At this point, I have two things left to do. I need to figure out what c equals, and then I need to solve it for y. It's going to be easier to, right now, plug in 0 and 0, because that's the initial condition they gave, solve for c, and then go back and solve it for y. So I think that's what I did next. It says now use 0, 0 to solve for c. So let's see, I plugged in 0 for y and 0 for x. That's what I did in this line. And luckily, e to the negative 0 is just 1, and e to the negative 2 times 0 is both one. Like both of these turn out to be 1, which is kind of convenient algebraically. So I have negative 1 equals negative 1/2 plus c, and I add a half to both sides. I get c equals negative 1/2. So now I'm going to go back to which line? This line. I'm going to rewrite that, but I now know that this c is negative 1/2. So I did that over here. So it's negative e to the negative y equals negative 1/2 e to the negative 2x minus 1/2. All I did was replace that c with minus 1/2. Now, what I did, the next line, you'll notice it says the natural log of both sides. What I did first is I just multiplied everything by negative 1. Everything in this first line, like everything is negative, I wanted to make it positive. So first I multiply everything by negative 1. So that got rid of some negative signs. And then I natural logged both sides, which I did here in red in this line. And my left side, the natural log of e to the negative y, just becomes negative y. The right side, I just left as one big, ugly natural log of the whole thing. And then I think all I did was, it says negative y equals, I wanted to say y equals, so I multiplied everything by negative 1, and I got to there. Yeah, I just stopped there. There's no reason to go any simpler than that. So there's your example of finding a particular solution. And your homework for this is 391, 1 to 27 odd. So there you have it. That is the end of the notes for 5-3, I think it was. Have a great Tuesday. I look forward to seeing you all at the live lesson on Wednesday.